can't drain the water. The figure below shows a water tank that is closed at the top. The 2-meter tall tank contains 1.5 meters of water, and the rest is air at a gauge pressure of 200,000 pascals. You attempt to drain the water tank through a faucet or tap located 10 centimeters above the base of the tank. The faucet has a circular opening with a diameter of 1 centimeter. We are to determine the speed of the water at the exit of the faucet, the speed of the water at the highest point in the tank at the same moment as in the previous part of the problem, and also to consider why the water stops flowing after the height has dropped significantly. This is a fluid problem, and we'll analyze it using the Bernoulli Principle. To apply the Bernoulli Principle, we select two locations within a single fluid and connect them using Bernoulli's constant. The two locations that I've selected are the top surface of the water, where it is in contact with the air, and the exit point of the water as it leaves the faucet. The Bernoulli Principle tells us that the pressure added to 1/2 density times velocity squared plus density times g times height y is a constant at all locations throughout any single fluid. The way we construct an equation using the Bernoulli Principle is to do this at the two locations, location 1 on the left-hand side of the equal sign and location 2 on the right. In this problem, the 200,000 pascals that we've been given is known as a gauge pressure. A gauge pressure is that pressure that is measured via a gauge. Take, for example, the instance of having a flat tire. If you were to walk up to your flat tire with a tire gauge and place the gauge on the tire, you would read that the tire pressure is 0. We know that in an absolute sense that isn't true. The tire pressure is actually 1 atmosphere. Gauge pressure is the pressure difference between the absolute pressure and 1 atmosphere. If we choose to do this problem in gauge pressures, then location 1 will have a gauge pressure of 200,000 and location 2 will have a gauge pressure of 0. If we choose to do the problem in absolute pressures, then location 1 will have a 300,000 pascal absolute pressure and location 2 will have a 100,000 pascal absolute pressure. We'll do it in gauge pressures because that typically makes problems simpler when they involve fluids that touch air. So the pressure at location 1 is 200,000 pascals. Because the tank is 1 meter breadth and the faucet itself is only 1 centimeter, I'll be able to neglect the velocity at location 1 as compared to other terms. We'll come back to this question of whether that's valid in part B of the problem. Location 1 has a particular height, and the value of that height depends upon where we decide to place y equals 0. Although you might be tempted to place y equals 0 at the bottom of the tank, location 2 is the lowest point we're dealing with, and so I think I'm going to place it here. If you had placed it at the bottom of the tank, you would have 1.5 meters on the left of the equal sign, 0.1 meter on the right of the equal sign, but in my case I will only have density times g times 1.4 meters on one side of the equal sign. Both of these will lead you to the same solution and would earn you full credit on any exam. For the right-hand side, since we're using gauge pressures, the place where the fluid touches the air has a pressure of 0, the same as the air itself. The kinetic energy term here cannot be neglected. It will be 1/2 the density times the velocity at location 2 squared. And by our choice of y equals 0, we have no potential energy term at location 2. This equation has only one unknown. That one unknown is v2, and plugging in the known values, we solve to obtain a velocity of 20.72 meter per second. Part B of this problem asks us to determine the speed of the water at its highest point in the tank at the same moment as in the previous problem. Students are frequently puzzled by this calculation, and so we're going to spend a moment explaining it. In part A of the problem, we used a velocity of 0 at part 1. The reasoning by which we justified this choice is that the term 1/2 rho times v1 squared was negligible as compared to other terms in the problem, and therefore leaving it out did not cause a mistake. We didn't say that the velocity at location 1 must be 0, because if it was, no water would possibly drain from the tank. Let's give the following analogy. Suppose I wanted to calculate the force of gravity on me. I might begin by trying to learn the mass of the Earth. I could leave my own weight out of the mass of the Earth and still get the correct gravitational acceleration g, but then when I wish to determine the force on me, I could no longer neglect my own mass, because that's the only one I'm talking about at that stage in the problem. Similarly here, we neglected the velocity at location 1 when we were comparing it to other terms in the Bernoulli formula. Now that we are asked to determine that value, our previous result is still accurate to many decimal places, and we simply stop ignoring this quantity because we're now needing to compare it to itself. The principle by which we make this determination is using something called the continuity equation. The continuity equation essentially tells us that mass must be conserved. When we analyze a Bernoulli equation and look at a term such as 1/2 rho v squared, we refer to it as the kinetic energy term, but in fact it's not in joules. Since it has a density instead of a mass, it is in joules per cubic meter. And so something we took for granted in our energy problems, that we conserved mass, is not apparent in the Bernoulli equation. Instead, it must be imposed by us. This can be imposed in two different ways. To impose directly the conservation of mass, we would say that the mass per unit time, kilograms per second, at any one location in the fluid, is equal to this same quantity passing by the next location in the fluid. This is the continuity equation that we would use in the case of gases, where the density could in fact be very different depending upon the pressure at various locations. However, when we deal with liquids, we make the approximation that the density does not change, and therefore we cancel it from the two sides of this equation, yielding the alternative form for the continuity equation that area times velocity at location 1 is equal to area times velocity at location 2. This time we won't neglect the velocity at location 1, and so in fact we will solve for it. Both location 1 and location 2 are circular apertures, and so their area is pi times their radius, 0.5 meters at location 1 squared, and 0.005 meters at location 2 squared. And filling in the terms, the unknown velocity at location 1 can be determined using the known velocity at location 2, solved for in the previous part of the problem as 20.72. This yields a velocity at location 1 of 0.002072, which clearly, when squared, is easily neglected in the previous part of the problem to get the right result. Only you can't neglect any quantity as compared to itself. In part C of this problem, we're told that the water stops flowing when the water level drops to a height of 0.91 meters. What is the pressure of the air in the tank at this point? And explain using one or two short sentences why the water has stopped flowing. Many physics professors would tell you that since the water is not moving, we should use Pascal's law instead of the Bernoulli equation. I'm going to tell you exactly the opposite. Pascal's law is simply what you get when all the velocities in the Bernoulli equation are 0. So rather than learn two laws with, unfortunately, two different conventions for which way is up, let's instead just stick with the Bernoulli equation, get the right answer, and not worry about Pascal's law. The technique by which we use the Bernoulli equation is, as always, to identify two locations and to connect these two locations using the Bernoulli quantity. That quantity includes the pressure added to 1/2 density times velocity squared added to density times g times y. And according to Bernoulli, this quantity takes the same value at any two locations within one fluid, and so we do this at location 1, and we do exactly the same thing at location 2. Just as we did in Part A, we'll continue by using gauge pressures for our units. The gauge pressure at location 1 is what we're trying to find, so we'll leave that as a variable. There is no motion of fluid at any location, and the height at location 1 has now dropped below the previous level. We'll continue to use y equals 0 at the top of the faucet, meaning that the height at location 1 is 0.81 meters. As before, you could have used this as 0.91 and put a 0.1 meters on the other side of the equation. In gauge pressures, since the fluid is in contact with air at location 2, it has the same pressure as the air, which is a gauge pressure of 0. It isn't moving, and it's at a height of 0. This means that the pressure at location 1 is now equal to negative 7,938 pascals. When we see a negative pressure, we need to express a little bit of concern. Fortunately, since we've chosen gauge pressures can be anywhere from negative 100,000 to infinity, and so as long as it hasn't gone below negative 100,000, we're okay. This also explains how it is that the fluid has stopped flowing. The fluid stopped flowing because as the water level dropped, the pressure above the water became less and less and less, and eventually it became below 1 atmosphere, thereby sucking on the water and preventing it from coming out the tube. If you've owned a hamster or a gerbil or a similar small animal, you've probably seen this effect already. This is exactly how the water bottle attached to their cage operates. The vacuum or partial vacuum above the water itself is what keeps the water from draining out, and it requires your animal to lick the water tube in order to send bubbles up into the bottle so as to release the water and then be hydrated.